Welcome to The Explainer, where today we're tackling a mathematical challenge that has stood for centuries. We're talking about a math problem that for a long time was considered basically unsolvable. But now there's a groundbreaking new method that claims to have finally found the key.
So, just take a look at this beast of an equation. It's an 18th degree polynomial. Now, for forever, pretty much, the best you could hope for was an answer that was, close enough, an approximation. But today, we're going to explore a new theorem that says, forget close enough. It claims to deliver a perfect, exact solution.
All right, here's how we're going to break this down. First, we'll look at why this problem is so tough. Then we'll talk about the huge difference between getting close and getting it exactly right. We'll introduce the revolutionary new theorem, peek under the hood to see how it works, and then the big reveal, the solution. And finally, what this all means for the future.
So first, let's just set the stage a little. These high-degree polynomials, they aren't just homework problems. They pop up everywhere. They describe the orbits of planets, the way financial markets behave. Basically, they're part of the language of the universe. So being able to solve them accurately isn't just a nice-to-have. It's absolutely critical.
Okay, so you might be thinking, why not just let a computer handle it? And you can. But here's the catch. Most of the time, that computer gives you an approximation, an answer that's almost perfect. We're about to see the massive difference between being almost right and being exactly, mathematically, flawlessly right. And this slide really gets to the heart of it. On the left, you've got the old guard, things like Newton's method. They're powerful, for sure, but they're basically really sophisticated guessing machines. They get closer and closer with each step, but they're always tiny rounding errors. But on the right, Azuide's theorem is promising something totally different. It's not about guessing. It's about finding the precise symbolic answer, the perfect formula, not just a number with a bunch of decimals.
And that brings us to the breakthrough at the center of all this, a theorem that really challenges some of the things we thought we knew about math.
This is a huge claim. Abel's impossibility theorem is a cornerstone of algebra. It's a famous mathematical proof that basically says you can't create a universal formula to solve equations of the fifth degree or higher. It's been considered a fundamental limit, and yet this new method says, hold on, I found a different path, a new process that gets us to an exact solution.
So what does that really mean? The key here is that this isn't about using a bigger computer or more brute force. It's a structured, almost elegant, step-by-step process. It doesn't just solve the problem, it actually transforms it, revealing a kind of hidden simplicity that was there all along.
So how in the world does it actually do it? Let's pop the hood and see what makes this thing tick.
Now, we are not going to put the actual formula on screen, and trust me, you don't want to see it. It's a lot. But the important thing is what it does. Its job is to take the numbers from our original, messy polynomial and use them to calculate a brand new set of 18 special numbers called S-values. And these S-values, they hold the key to everything. So the process starts, and it calculates these S-coefficients one by one. Each new calculation actually depends on the one before it. And what it finds is, well, it's pretty weird, and not at all what you'd expect. The process kicks into gear. It calculates the first S-value, and it's 0. Okay, then the second one, also 0. Then the third, the fourth, the fifth, all the way up to the 8th one. They're all 0. At this point, you're probably thinking, what is going on here? Is this thing even working? But then, wham! On the 9th calculation, sveit dir, the formula spits out this gigantic non-zero number. And this is the first real clue. It's a sign that there's a hidden structure here, and we've just found the first piece of the puzzle. So you'd think, great, we're on a roll. But then, the weirdest thing happens. The very next calculation, it's back to 0. And the next one, and the one after that, all the way from S9 to S16, nothing. Just a string of zeros again. And just when you think you've lost the trail, on the final calculation for S17R, bam, there it is. Our second and final crucial piece of the puzzle. We now have 2 non-zero S-values, and it turns out that's all we needed. All right, now for the grand finale. This is where it all comes together. This is where we see how those two little numbers completely change the game. Okay, remember this absolute monster from the beginning? All those terms, all that complexity, just this huge, tangled mess of an equation. Well, watch this. Because almost all of our special S values were 0, they effectively go in and, poof, just wipe out 15 of the original terms. And that massive complex equation just collapses into this, a beautifully simple equation with just 3 terms.
It's the exact same problem, just seen through a new lens that reveals its true, simple shape.
And from that super simple equation, we get this. Okay, I know, that still looks like a beast. But here's the thing, and this is the most important part. That isn't a close answer. That is the perfect answer. Every single number and symbol in there has a precise value. It's the exact symbolic solution.
So, why do we care? Why does solving one crazy, complicated math problem actually matter so much in the grand scheme of things?
You know, this is about so much more than just this one equation. It's about a new tool in the toolbox, one that offers perfect precision in places where we used to have to settle for good enough. Think about fields like quantum physics or cryptography, where the tiniest approximation error can have massive consequences. This could be a total game changer.
And ultimately, that's maybe the most exciting takeaway from all of this. It just makes you wonder, right? What other problems that we've all considered impossible for decades, or even centuries, are just waiting for someone to find a new way to look at them?